So I'm going to talk about Voronoi diagrams this morning, and maybe some of you don't know what those are, so I'll take you through some of the basics. And there's no more appropriate place than London to talk about Voronoi diagrams, because one of the first instances of modern epidemiology used the form of Voronoi diagram to look at the cholera outbreak in Soho about 150 years ago. And so this is a map of Soho back in the day, and I've overlaid blue dots onto the locations where there were water pumps, so people would go there to get the water that they needed. And then the black bars that are shown on these maps, those are fatalities. So people died in the residences at those locations, and so some of these locations that have a lot of black bars, there's a lot of fatalities there, and less fatalities at the locations that have sort of a smaller bar chart at that particular location. So what John Snow did is he actually determined how long it would take for someone to walk to one of these water pumps, and then manually drew this region here that you can see around that central water pump. And this is on Broad Street, which is now I think is Broadwick Street. And he determined that most of the people most of the residences that had people dying were closest to that particular water pump. And so this is actually a sort of crude example of a Voronoi diagram, but a very useful example of its application in modern epidemiology. So most of those people were getting their contaminated water from that particular pump. And just as a sort of fundamental concept, what you want to do with Voronoi diagrams is to identify the points in space, so in this case it's just the planar XY Cartesian space, that are closest to a given pump or a given generator. So we use the term generator in the field to refer to an original data point in the data set. But this is not, so the region that John Snow drew manually, it doesn't look like a Voronoi region does in most of the modern diagrams that you'll see. So that's because his is a walking time based Voronoi diagram. And most of the Voronoi diagrams that we make now are Euclidean distance based, so those will be truly convex Voronoi regions. So I'll tell you a little bit more about that later. So Python actually, this wasn't the case a few years ago, but now SciPy, this is the popular scientific Python library, actually has some great utilities for doing Voronoi diagrams and some other computational geometry techniques right out of the box. So there's this set of data. So this is the data from 150 years ago, but curated for data journalism. So there was an article in The Guardian a few years ago, and then there's an academic's blog, Robin Wilson's blog at the University of Southampton, provided the raw data to work with this in 2015. So I just thought I'd create an actual Voronoi diagram overlaid on, so those black bars in the maps are now being shown as red dots whose radii are proportional to the number of deaths at those residences. And this is the actual Voronoi diagram, so now you can see the convex cell in the map here. So everything within that convex cell right here is closer to the pump on Broad Street. But you can see that you can see that there are residences with mortalities that could actually go to a pump that's somewhere else. And so there was actually a bit of data journalism involved. So John Snow had found out that there was a lot of anecdotal evidence for people at those locations preferring the water from the infected pump for whatever reason. They thought it tasted better, or that kind of thing. So that explains that particular, at least most of the outlier data sets in that particular diagram. But yeah, so there's this scipy.spatial.voronoi that actually didn't exist when I first started working on this a few years ago. You just feed in your pump coordinates, so the blue dots, so just feed in those coordinates as a numpy array. And then there's actually now a built-in plotting function, so you don't even have to do too much work. You just take scipy.spatial.voronoi plot2D, and you feed in the Voronoi instance object that you created, and that'll produce a plot for you. So it's quite convenient now to produce simple planar Voronoi diagrams in 2D Cartesian space, so for a map, for example. And so this is just one possible application of Voronoi diagrams. You can also imagine things like looking at cell phone tower coverage, or in marketing if you want to know which stores are closest to where people are. There's all kinds of applications for Voronoi diagrams in the plane. And this is just one particularly compelling example because it involves sort of public health on a large scale. And so planar Voronoi diagrams have been studied for quite a long time. I mean, computational geometry in general is quite young. So the early 1970s is pretty much when it started. So very early on there was already already an established algorithm, this divide and conquer algorithm, which is this is still the optimal performance. So this O notation means the time complexity, how long it takes to run this algorithm, where n is the number of input data points. In that particular case, n would be the number of those blue pumps. So this is the sort of the upper time limit. So this is a log linear time. Slower would be this quadratic incremental algorithm, which was discovered a few years later. There's also this quad edge data structure algorithm, which I don't know much about, and the famous Fortune sweep line algorithm. So Steve Fortune was working for Bell Labs at the time, I think, and he came up with a great algorithm, really efficient algorithm, which actually basically just sweeps a line across from left to right, and it produces the Voronoi diagram on the left side, and then it still has to produce, so it's sort of progressively producing the Voronoi diagram as it moves from left to right across. But it turns out actually that, and this is one thing that I found when working with different Voronoi diagrams, is that sometimes the most efficient implementation isn't the one that becomes the most popular. So it might be slower, but if it's easier to implement, that's a really important thing. So it turns out that this incremental algorithm, the quadratic one, so as you have a quadratic time complexity, if there's a lot of data, it can be quite slow, but because it's easy to implement, it's become one of the most popular implementations, even though it's a little bit slower. So SciP uses the QHull library. This is a popular computational geometry library behind the scenes, and it does say that in the documentation. So if you look in the notes, so it'll say that it uses the QHull library, and it says it computes the Voronoi diagram via the Delaunay triangulation, which is the mathematical dual of the Voronoi diagram. And if you don't know what that means, I'm going to tell you, so don't worry too much about that. So there's just one or two concepts in computational geometry that I should go through before I get onto the spherical Voronoi diagrams that I've been working with. One of these concepts is the convex hull. So if we just jump right to this, the picture here of what the convex hull is in 2 dimensions. If you think of for example, a wooden board with nails placed in it. So each nail is representing one of these data points, one of these blue dots. If you took an elastic band and wrapped it around that set of nails, that would be sort of a visual demonstration of the convex hull. Now humans, we're actually pretty good. You can actually probably just by eye pick out the points that are forming the outer boundary of this structure, this convex hull. But computers aren't so good at that, and as you go up to thousands and thousands of points, even for the human eye, it would become quite difficult to identify the convex hull. So there are algorithms for doing this. Once again, one of the slower algorithms, the incremental algorithm, I think this was actually published in 1972, and it was the first computational geometry paper ever, apparently. So this is a quadratic time complexity in both 2 and 3 dimensions, but it's often implemented just because it's simpler than some of the others. And again, log linear, these are the most efficient algorithms. There's actually this GIF wrapping algorithm, which is kind of interesting because its time performance actually depends on the number of points in the hull. So here there's actually points that are internal, and then points that we say are on the hull, so they're right on the edge there. So if all of the points in the data set are on the hull, then this algorithm is actually slower. So it's output sensitive in terms of its performance, which is just something I hadn't seen before. But in any case, incremental, it seems to be implemented most often. I haven't checked what's going on with the QHull Python implementation, but because it allows you to add additional points after you've done the initial calculation, I suspect it has to be the incremental algorithm, which is quite tolerant for adding an additional point after you've done the initial calculation. But as with Voronoi diagrams, it's now quite easy to do convex hull calculations in Python, again using the popular SciP library, scip.spatial.convexhull. And there's also a convenience plotting function, so you just take the hull object that you got by calling the SciP convex hull on your original data points, then just plot it in 2D. You don't even have to write the plotting code, and you get a nice plot out of that. So that's quite convenient. 3D hulls, it's the same sort of concept. So you have and here I've just taken a random set of 3D points. You have to do the plotting yourself, but it's not too big of a deal. And here, instead of it being like an elastic band around a planar set of points, it's more like sort of like a plastic bag around points in 3-dimensional space. So it wraps right tightly around them, and you have these faces or these facets that form the sort of faces of the polygon that surrounds those points in 3-dimensional space. So another really important concept, and this is directly related to Voronoi diagrams, is the concept of triangulations. And if you can actually define triangulations without using the word triangle, so it's basically just the maximum number of edges that connect the data points in your original data set that don't cross, so non-intersecting edges. So it's really this really simple definition. But it's actually amazing, there's still a lot that we don't know about triangulations, even of planar points in in two-dimensional space. So here T is just the total number of triangles. K is the number of interior points, so the points that are not on that convex hull, and H is the number of points that end up in the convex hull. So you can see that for a given set of points, T, the number of triangles, and planar triangulation is always fixed. It's always the same number of triangles. However, we don't actually have a great way to figure out the number of like how many different triangulations with that same number of triangles exist. So just recently, 6 years ago, we found out that 30 to the power of the number of data points is the maximum number of triangulations. That's a lot of triangulations. So this is still a very nascent field, even though it seems like a really simple concept. You're just connecting these points in a plane. So what's really interesting from the standpoint of what I do and for what people working on Voronoi diagrams is this idea of the Delaunay triangulation. It's considered, and this is the technical term, it's considered the fattest triangulation. So you basically take the triangles, you take the triangulation that avoids really skinny triangles. So like from a programming standpoint, you do like a lexicographic comparison. So you take all of the angles. So if you go through each of these triangles, take all of their angles. So just one flat list of all of those angles. Then you compare. So if you compare two different triangulations with those two flat lists, the first one that has an angle that's smaller than the other is considered the skinnier triangulation. So the fatter triangulation avoids really small angles at the start of that list. In other words, it avoids really skinny triangles. And that's actually the formal nomenclature for this sort of thing. And you can actually build different triangulations just using edge flipping. So if you imagine, just take this edge right here and then erase it and draw it from this vertex to this vertex, that would be an illegal edge. We would say it's an illegal edge because it generates a really skinny triangle. If you imagine the triangle formed between this vertex and this vertex, it's a really skinny triangle. And what the computer would do is just actually do that lexicographic comparison where you'd have the really skinny angles here, and it would reject that as not being the Delaunay triangulation. And again, SciP provides a really useful Delaunay class object, and you can just feed that in and you'll get the Delaunay triangulation for your 2D point set right away. So that's quite useful. Another definition of the Delaunay triangulation, which is really, really useful for Voronoi purposes, is that it always excludes the original data points from the circumcircles. So if you take any given triangle, like this one here, this big one at the edge here, and draw a circle that has its outer line going through those 3 points, none of the original data points will actually be found in a given circle. So it's a bit hard to tell in the middle here because it's so dense, but you can see here that there's no original data points that are actually falling within the circle, they're just on the edge. So that's also part of the definition, an alternative definition of these Delaunay triangulations. From a practical standpoint, Delaunay triangulations are considered the best way to do terrestrial reconstruction. So if you want to have these like fancy maps of the Earth's surface elevation is only measured at certain points, and you want to sort of triangulate that to make a nice smooth map, Delaunay triangulations are considered the best way to do that. There's also these minimum weight triangulations, which are used if you were building like a network of actual physical wires connecting nodes. If you wanted to reduce the amount of wire because that wiring is expensive, for example, there's a type of triangulation that can be used to tell you which connections to make to reduce the amount of wire involved there. So that can actually be quite useful as well. But for my purposes, what's really interesting is that because the Delaunay triangulation is the mathematical dual of the Voronoi diagram, you can actually connect the centers of those circumcircles. So again, these are the circles that you draw through the triangles from the Delaunay triangulation. If you connect all of those together, you get the Voronoi diagram, which is really quite useful. So they're connected in really deep and interesting ways. And it also turns out that Delaunay was Voronoi's PhD student many years ago at Kiev University, so also connected in that way. And the convex hull is also beautifully connected to the Delaunay triangulations and the Voronoi diagrams. I won't say too much about that, but it will come up in the spherical Voronoi algorithm that I go through. So before I sort of start going through the algorithm that I've used for the Python implementation of spherical Voronoi analysis, I just thought I'd motivate it with what I use it for and what other people could and do use it for. I'm a computational virologist, so I build models of viruses, not computer viruses, but viruses that make people sick. So this is a model of influenza A virus. So it has these spike proteins. The orange ones, these are actually the hemagglutinin proteins. So those latch on to sugars in our respiratory tract. So someone coughs or sneezes, that's how it sort of attaches into our respiratory tracts and infects us. I put it in a water droplet, and it sort of wiggles and jiggles as I do these simulations. And I can use Python to parse that motion over time to try to gain biophysical insights into this pathogen. So this is just a snapshot of a Voronoi diagram on the sphere. These sort of larger yellow points are for these large proteins. This is a really zoomed in region, so it looks almost planar because I've zoomed right into the surface. And here you can actually see the individual Voronoi cells. Yellow is the protein. Green is actually cholesterol. So it turns out that flu actually takes a lot of cholesterol from our bodies when it buds off. It provides sort of a structural rigidity. But okay, that's what I do, but probably a lot of you aren't doing that from day to day, but there are actually a lot of other potential uses for spherical Voronoi diagrams. It turns out, so Jason Davies, maybe some of you might even know him, he's in London, I think he's a data science consultant, and I think a year or two after I started doing spherical Voronoi research, he wrote what seems to be a JavaScript implementation of spherical Voronoi diagrams. So you can actually go on and sort of interact with the diagram, but you can't provide input data and get output with like the actual spherical Voronoi diagram, so you could do calculations with it. It seems to be closed source, but nonetheless, it shows you this is our planet with all of the airports forming the initial generator points in a Voronoi diagram. So you can imagine applications like search and rescue. So what's the closest airport to a grid in a search and rescue situation? So Voronoi diagrams provide a really convenient way to access that information. If you're living in a country that sort of has regular problems with sort of Russian aircraft infiltrating airspace, and you want to know what's the closest airbase to dispatch a jet, which is probably a really expensive thing to do with taxpayer money, you might want to have a spherical Voronoi diagram on the surface of the Earth for that purpose. Global epidemiology, so looking at disease outbreaks, telecommunications, so network coverage and that kind of thing. All kinds of potential applications, probably many that I haven't thought of for spherical Voronoi diagrams. So when I was looking to do this in Python, because there was a paucity of open source resources for doing spherical Voronoi diagrams, I looked at the primary literature. I'm an academic, so that's sort of my intuition. I actually did know about this older paper, so I went straight to a more recent paper which used a stereographic projection. So that's basically you project the coordinates from the sphere onto a plane, and then you do a planar Voronoi diagram, and you project back up, and then you do some more work, and then you project it back down. So you do 2 planar Voronoi diagrams. I spent a few months, probably way too much time on that, and I did not have any success. It turns out that again, as with the planar case, the maximal performance is log linear. But I just had a lot of trouble looking at the primary literature. And so I went to the internet, which is, I guess, sort of the last resource, but also potentially the most useful resource. And so Stack Overflow, just someone sort of innocently made this comment. And then I also found that there's a closed source, I think this is Wolfram's Mathematica, applet, where you can click on a sphere, and it sort of made me feel kind of bad because there's just, almost like a sort of a childlike exercise, and they just explain how it works. But I thought we needed an open source implementation regardless, and also because this, again, it's just sort of an online thing where you can click on it, but not really interact with it in a meaningful way, where you put in your data set and then you get out your Voronoi diagram, and then you calculate, for example, the areas of the different regions and that sort of thing. You want something that's malleable that you can work with your own data, do data munging with it. But certainly the internet played a big role in sort of suggesting that if you compute the convex hull on a sphere, on a perfect sphere, that's equivalent to the Delaunay triangulation. And then if you take the normals to the faces of the convex hull on the surface of the sphere, you get the Voronoi vertices. That's a much, much easier algorithm than any of these papers have implemented. So I thought I would try that. So that forms the basis of the implementation, which is open source. I just put it up on GitHub a few months ago. It's also, I like to think it's well documented. I spent a fair bit of time writing the doc strings and describing what it does. There's also some detailed notes section which I've clipped out here, which talks about some of the limitations, and also tell you about some of the limitations and some of the areas where I'm hoping to get maybe some advice on some of the weaknesses of the algorithm and the problems with the code. There's also an example here, which I think you can probably just copy and paste into an IPython notebook, and it should work right away. You can see the result for I think 1,000 point random data set looks quite reasonable. So you can see the sort of the Voronoi cells on the surface of a sphere. So I was quite happy with the initial, at least with the initial outcome of the code. So I'm going to go through step by step. There aren't too many steps to this algorithm, but just to show you how I did it. I think I've taken a few liberties with the sort of the indentation. So I know Python, of course, obviously depends strongly in indentation for clarity, but here, just for the purpose of the presentation, I've made a few adjustments just so I could fit it all together. So basically, I just took 1,000 random points on a sphere with a radius of 1. This is a function in the open source code that I have. It turns out that generating random points on a sphere is actually its own field of mathematics. And I probably still haven't done it perfectly, but if you try to do it naively, it turns out that almost all the points end up on the poles, which is really, really annoying. So I think I've almost got it right, but all I wanted to do was just pin down. And I've also pinned down so I've used a random seed that I've pinned down, because it turns out there's actually pathological input. So if you have points that are co-circular, I think that's pathological. So you have to have certain requirements on the data input. So real data is often okay, but if you just start working with random data, you can end up with some pretty pathological. Obviously, you can imagine like 2 points are practically on top of each other. That's going to cause like floating point problems when you're doing calculations. So thanks to the internet, we know that the Delaunay triangulation is equivalent to the convex hull. So we can use the built-in convex hull on the three-dimensional points on the surface of the sphere. Here I'm just working with random coordinates. Could probably get rid of this for loop. So just you'll forgive me for that. The code's still in its sort of early conceptual stages where you sort of work with for loops and then get rid of them when you optimize later on. But basically just going through all of the triangles in the convex hull and just collecting those points into an array which basically has n triangles which are in three-dimensional space. So it has the 3 vertexes with their x, y, and z coordinates. So the generators, the original data points are in blue, and then the triangulation, the edges that connects to those points, the Delaunay triangulation is shown in red. Now this big wall of code is basically just calculating the normals, so the lines that go from the sort of the center of the sphere through the triangles in the Delaunay triangulation, and those end up being the Voronoi vertices. So it's kind of painful how close we are to the solution already. So we have our original data points in blue, and the vertices, the points that form the Voronoi diagram that we want, in green. Now here's where I really actually have a lot of problems. So we're really close to the answer, but the challenge is associating the Voronoi vertices, so the points in green, with the data points that they're supposed to surround. And also, we have to order the polygon vertices that are in really close proximity. That can be a little bit tricky. And you'll see that I had some problems with missing vertices. I'm just wondering if there's a better way to do it than I've chosen to do it. So maybe keep that in mind as we go through the small number of steps that are involved. So the way I ended up doing it was basically to take, we know that each Voronoi vertex is equidistant to at least 3 of the original generator points. So you can see basically one of these Voronoi vertices, green, is equidistant to 3 points. So this is shown for 2 random points I've taken out of the code here. So this is the result of the code. So the code just basically generates a distance matrix up here using SciPy's c-distance method, and then parses that distance matrix to figure out which are the closest original data points to a given Voronoi vertex, and then make sure that there's at least 3 of those as an assertion here, because if it doesn't, then there's something wrong. And then we know which original data points are closest to a Voronoi vertex. But what we actually want to know is which Voronoi vertices should surround a given generator. And so this is done using Raymond Hilliger's collections module to speed things up a little bit. And so basically, you can see that there's at least one case here where it actually works quite well. So we've connected the dots, the vertices, quite nicely around the original data point. In one case, it looks like it's a terrible situation because the generator is nowhere near the polygon that's supposed to surround it. And in one case, it looks like this is salvageable. It's just the vertices haven't been ordered properly yet. So that's something that we can deal with in the next step of the process. So,
sorry, this problem occurs in the spherical case, or can this occur in any case?
This is just for the spherical case. So in the planar case, that shouldn't occur. where you have this shouldn't happen in the spherical case either, but it's happening with my particular.
Solve the question why that happens.
No, I'm certainly concerned as to why that happens. Yeah, there's a question there too. Yeah. I tried both. Yeah, so it turns out the chord length, which actually goes through the sphere, is directly related to the arc length anyway. So I didn't find any difference because you just plug it into equation and it works out to being the same effect actually. And then finally, I can sort. There's various ways to sort the vertices of the polygon, and so we see here that for this pathological case on the right, that was actually sorted out. So now this is a nice convex polygon. But for the case on the left, although we have a convex polygon, the generator is not contained within it. So that's an issue. Nonetheless, overall, the diagram doesn't look too bad. More than 95% of the surface area is reconstituted. So if you take all of these polygon areas and set them together, that adds up to roughly what you'd expect for the surface area of a sphere of that radius. But we do have these issues. And if we look at example results, so this is an actual result where you can see there's these little blank spaces. So Voronoi diagrams definitely should not have these blank spaces. That's one. It looks fairly minor in that case. If I take a more pathological case, you can see that the blank spaces are a little bit bigger, so that's a bit of an issue. I've also had some problems, so if you want to calculate the surface area of these polygons, so if you just assume that they're planar, that's fine, that works reasonably well. But if you want to actually calculate, because these are actually curved polygons on the surface of a sphere, if you want to deal with these angles on the surface of the sphere, it actually seems to be quite unstable to sort of floating point issues. So people have suggestions. There's certainly equations for dealing with this, but they still seem to be sensitive to issues if the points are close enough together. So just two sort of small conclusions. So ultimately, in a fairly small number of steps, I have the Voronoi vertices on the surface of the sphere. And the challenge seems to just be to take that data. So we almost have the answer. We just need to know how to connect the answers to form the diagram. And maybe someday spherical Voronoi will be possible in sciped.spatial, but if people think that's useful. So that's all I have to say.
Thank you, Tyler. Right, so we're running well in time. The chaps next door finished early. That's why you heard the clapping. Any questions for Tyler about Voronoi diagrams?
Yeah, one. Thank you for the nice presentation. I just wanted to make a comment for generating the dots near the poles. So I think the distribution, when you generate a theta angle, it has to be uniform not in theta but in sine theta, and you'll get a uniform distribution over the theta angle.
We're talking about putting the points nicely over the sphere. Yeah. There's a few papers I've seen about it. But
it's just if it's uniform in theta, then because sine is changing rapidly towards higher values closer to 0, you have much more values closer to 90 degrees.
Right, which is why you get the polar bias.
That's why you have to take a transformation of sine theta and take the distribution of sine theta, and then so it has to be uniform distribution of sine theta. You can generate a random number between 0 and 1. So, but we can talk later about that.
Sorry, do you have an addition to that?
Yeah, so if you want to generate a random point on a sphere, you have a number of dimensions in the two
alarm system,
and then each one, if you generate a Gaussian distribution, you get a random vector, and then you project it onto the sphere. It's a random point. It's a really good trick. Yeah, it's a really good trick.
Yeah.
I have a question. So I work in, I've done a lot of work with looking at lung damage, and cells often form what look like Voronoi diagrams. So does any have building generating Voronoi diagrams is sort of one way of going? Do you have equations for going backwards, analysing Voronoi diagrams and seeing how they change over time? It would certainly be the kind of thing where it's very hard to do quantitative analysis of tissue damage, but invariably it's if cells in a given system die, so analysis of Voronoi diagrams would be quite useful for being able to analyse how much damage has been done in a given tissue. Is that something that Voronoi diagrams tackle?
So, I mean, my data is all time series based, so I basically calculate the Voronoi diagram at each time point.
Yep.
So the virus is moving around in water. So I can actually calculate the size of a given Voronoi cell over time. So I basically track that over time. So that's one way to look at sort of how it's changing over time. But yeah, I think you'll always have the same number of Voronoi cells because you have the same number of generators, so that's going to remain constant. But you could certainly look at the fluctuation in the amount of area occupied by a given generator, which is the size of its polygon on the surface.
Okay, cool.
Yeah.
Any more questions? Lovely.
You said your algorithm is n squared, is that right?
Actually, I don't know from my algorithm. My first priority is to make it work, and then I'll start worrying about the time complexity. Yeah.
I was just wondering, roughly what kind of runtimes you get.
It's fast enough for my purposes, but yeah.
And that's with kind of 1,000 points or so.
Yeah, maybe 40,000 at the most, but yeah, it hasn't been a bottleneck. Yeah.
How long does that take?
Yeah, offhand I'm not sure, but it doesn't take too. It hasn't been something that I've noticed, anyways, in terms of the. So I haven't done much benchmarking. Yeah.
You said so. Your first priority is to make it work. So but you do know that this closed source implementation you mentioned at the beginning, that this has the same problem or not?
No, I'm not aware of this issue on any of the closed source implementations. So there's one in Wolfram, and then there's the one in the JavaScript.
Yeah.
So, but I don't have enough information. I can't zoom in, and I can't pull out the data and actually look at it in detail. But I suspect they don't have that issue. There are several papers in the primary literature, so maybe trying a different algorithm would work better. But
so do you think that the problem is somehow is it more like a coding problem, that there's a mistake in the algorithm, or do you think that this is a conceptual problem of how to do this in theory?
maybe a little bit of both, but I think it's probably primarily just like coding, just going from, I already have the Voronoi vertices, so just going from that information, you should be able to just sort of do the distance matrix and rebuild the Voronoi diagram. That's my general feeling. And just for some reason that's not working, and I'm not sure why. So maybe there's something really simple that someone could just point out and I've screwed up somewhere. I hope that's the case. I do hope that's the case, but I haven't found it.
So just to explain your algorithm, you used a convex hull of the set of points on the sphere, right?
Yeah, you do a three-dimensional convex hull, and then that forms the data set, the same data structure as the Delaunay triangulation.
There's a really good trick here as well, which you might find is a lot easier. So if you take your sphere, and then you add the center point, and then you build a Delaunay triangulation again, then you have a set of simplices, and all of them have the center point, if it's non-degenerate. Mm-hmm. Now, for each, if you look at the outside faces of those simplices, then each of those will be a face in the Delaunay triangulation on the sphere. Mm-hmm. Then you take the circumcenters of those simplices, and then you can project onto the sphere, and that gives you Voronoi vertices. Mm-hmm. And then if you iterate around each point of the the Delaunay triangulation, then you will get the simplices. You just have to do circulate around the points. Mm-hmm. I can explain this in more detail if you like, but.
Yeah, no, I'd definitely be interested in an alternative construction strategy.
I mean, so if you know QHull, I used to work for Seagull, which is the
library.
In Seagull, so I can tell you what we did if you like.
Okay, no, it'd be really useful. Yeah.
Do you have any more questions for Tyler before we break for a small break? Lovely. Tyler, you'll be around all day?
And tomorrow.
Lovely. Tyler's around all of the weekend. Do ask your questions to him then. Otherwise, we've got a break for the next 5-10 minutes, and then we'll start our next talk. So thank you very much, Tyler.
Thank you.